Okay, so thanks everyone for coming. I'm Mike Morrow. I'm the president of the St. John Center of the RASC. We've got lots of folks here. So we, many years ago, before COVID, we used to go around and introduce ourselves. So why don't we do that again? And then I'll try and go through and see who's online. So thanks everybody for coming. We've done the introductions. Our speaker tonight is going to be Anna O'Grady, who's spoken to us a couple times before, and she's going to give us an update on sort of her latest discoveries, and we'll get to that in a few minutes. We'll have some observation reports. We're going to skip the sky next month, but we'll tell you where to find it. And then we're going to go on at the end to some holiday themed refreshments. And so, see, I got to move the participants out of the way. So I do have a few announcements. So at the last meeting, I announced that I was going to talk about the Lucy mission this meeting, but Anna had a paper that I guess went up on archive, and is it submitted now or?
Oh, I accept it.
Accepted, okay. With some new results. So, and sort of on short notice, Anna agreed to, it turned out she was going to be here. And I guess Air Canada got you here. Is that who got? Amazing. And so we're really happy to be able to hear from Anna today. So I'm going to talk about Lucy in January. Here's an important piece of news. In November, we heard that guy, Gary, had an asteroid named after him. And that's quite an honor to have a rock floating around between Mars and Jupiter named after you. So congratulations, Gary. Very much deserved. One of the things that happened in November was the National RASC started some education and public outreach town halls and asked the Atlantic centers to present first. So there were a bunch of us, Randy, Gary, Robert, me, and Craig, I guess, who joined that meeting, and I did a presentation about the outreach we do. And there's another one coming up next week where I think Eastern Ontario is going to be presenting. And if you're interested in joining, I don't think they've, in seeing that, let me know and I'll send you the link to register. You have to register so that your Zoom link is personalized to you. But if you're interested, you can let me know. The other thing I just want to mention is many of you are aware of this Turn Off the Lights petition that Christina Smith has organized. It's a situation up in the Battery where somebody is very aggressively shining lights into neighbors' windows. And there's a few thousand people have signed that petition now. And she's actually gotten quite a bit of action. And there's actually an update today that she met with John Abbott, who's, I guess, the member for that district, and a minister, and with people from the city. And there seems to be a lot of determination to solve that problem. And so if you haven't already signed, I encourage you to do so. You can go to change.org and search for St. John's Turn Off the Lights, and that will get you to her petition. That will get you to her petition. And I didn't actually line that camera up very well. That'll get you to her petition, and you can also see some updates. Okay, so and for visitors, I just want to mention that our meetings are obviously open to the public. But there are lots of benefits of membership. There's a supportive community that is eager to help you learn about astronomy. We have a member chat group, which is very active. People have a lot of fun with that. People share observations, they discuss things, they talk about what is interesting to look at. A lot of mentorship on there, and you contact Randy in order to join that. It's for members only. There are the publications, which you can see down here, the Journal, Sky News, and the Observer's Handbook. And there's equipment rentals and member observing sessions. Not that many right now, but they're out in Butterpot, and maybe they'll pick up again next summer. And my mouse seems to be working on this screen, but not that screen. So that's probably going to be a bit of a complication. You may need to describe what you're pointing at, unless you can figure out how to fix that.
I'll jump and point.
Well, for the people online, it's a bit of an issue. Right? Okay, and members, you should be getting a weekly newsletter and a monthly bulletin. And that brings us to the main event. Which is Anna O'Grady. Her talk this time is Twists and Turns While Searching for Strange Stars. And many of you know Anna. She was a member of this center. She's a graduate of the physics department here, and she's a final year PhD student at the Dunlop Institute for Astronomy and Astrophysics. And she's told us before about Thorne-Zhitkov objects, which are red giants with a neutron star at the center, and super asymptotic giant branch stars, which I guess you identified the first population that was, really, that's really what they were. And it's sort of at the boundary between massive stars that will explode and stars more like the sun that will end up as white dwarfs. And so, as I said, sounds like she just had a paper accepted, sort of wrapping up, I guess, that part of the project. And so take it away, and I'm going to stop sharing so that you can switch which PowerPoint is working. I'll just stay nearby in case there's any issues.
Okay, so, okay. And can everybody hear me okay?
Yeah.
Back and on Zoom? Excellent. Okay. Well, first of all, I'd like to thank Mike for the invitation to speak to you all again. I'm absolutely thrilled to be back here. This is my third time giving a presentation. I'm sorry, this is my fourth time giving a presentation to the Royal Astronomical Society, Newfoundland, St. John's chapter. I first spoke here about projects that I did for my high school science fair, which was the first time that I had done astronomy projects. And then I've given two talks that have been sort of along the journey of this main project that has made up the bulk of my PhD thesis. So previously at RASC St. John's, these are the titles of the talks that I have given. So the first was on Thorne-Zhitkov objects, and the second, still on the same project, was called Identifying the First Population of S Super AGB Stars. So for those of you who haven't seen my first two talks, I'll be going over a recap and explaining exactly what this means. But yeah, so this is the central project of my thesis, and all of the excitement that came along with all this began with one little star. And it is this little light right here. This star is called HV2112, which is unfortunately not a very pretty name, but HV2112 is a very peculiar star located in the Small Magellanic Cloud, which is one of the satellite galaxies of our Milky Way. And it's a peculiar star because people aren't exactly quite sure what it is, and a few different identities have been prescribed to it over the years. In 2014, it was identified as the first Thorne-Zhitkov object candidate. And I'll explain what a Thorne-Zhitkov object, or a TZO, is in just a little bit, but this was a very exciting result about a decade ago. However, other studies have suggested different identities. It suggested that HV2112 might not be a Thorne-Zhitkov object, but it might instead be a massive or even super asymptotic giant branch star. So what do these words mean? So a Thorne-Zhitkov object is, in my opinion, one of the coolest objects that you can possibly get in astronomy. It is a red supergiant that has a neutron star at its core. So it is essentially a stellar turducken. It's a star inside of another star. These are formed when you have two binary stars, one a little bit more massive than the other. It evolves, explodes as a supernova, leaves behind a neutron star. And that neutron star, either because the supernova kicks it into its companion, or because the companion swells up into a red supergiant and sort of catches the neutron star falls into the center of the red supergiant and becomes its new core. These are predicted to look like red supergiants on the outside, except for a few key differences that I'll get to. But until 2014, these were theorized in the 1970s by Kip Thorne and Anna Zhitkov. And it took until 2014 for someone to identify something that they thought was a really good candidate. On the other hand, the other sort of prescribed identity that HV2112 might be is that of a super asymptotic giant branch star. And these are essentially the dividing line between low and high mass stellar evolution. So you have low mass stars. These are stars like our own sun. They burn hydrogen and then helium in their cores. They eventually puff off their outer layers, leaving behind a beautiful planetary nebula, and you're left with some kind of white dwarf. Then you have really big stars. Think like Betelgeuse, the red supergiant. Those will progress up to higher and higher burning levels. They'll burn magnesium and silicon all the way up to iron, which they then can't burn, which then causes a runaway collapse. The star explodes as a supernova, and maybe you're left with a neutron star, maybe you're left with a black hole. But the question is, where's the tipping point between those two very different fates? How big does a star have to be to not become a white dwarf, but instead become a supernova? And is there any sort of kind of middle ground? And those are what we call super AGB stars. These stars can burn carbon in their cores, but they don't progress further. And they either leave behind what I'll just call a very interesting looking white dwarf that doesn't look like the type of white dwarf our sun would leave behind, or it can explode as something very rare called an electron capture supernova, which I don't do that, but they're very cool. So either of these two identities for HV2112 would be fascinating. If it's a Thorne-Zhitkov object, that confirms that theory of stellar evolution. And it tells us a lot about binary evolution and different avenues of binary evolution that can happen. On the other hand, if it's a super AGB star, when I began this project, there was only one super AGB star candidate out there, even though we expect these stars to be about 8 to 10 times the mass of our sun. And you expect to be a fair number of 8 to 10 solar mass stars out there, but none had been confirmed. And if we're able to find more of these and understand them, that gives us the lower limit on core collapse supernovae. That tells us how many supernovae we think should be exploding in the galaxy. So either of these two identities are interesting. And when I began this project, I will say that the Thorne-Zhitkov object identity was preferred in the community. It was thought that there were some issues with the super AGB hypothesis. So we went into this thinking, if HV2112 is a Thorne-Zhitkov object, what can we do to better confirm that? How can we tell what it truly is? And we approached this, myself and my research collaborators, asking one particular question. Is HV2112 unique? Is it the only star like it out there? Or is it part of a larger population of similar stars? If you go looking, do you see more HV2112s out there, which would be very useful? It's difficult to study one star in detail, but if you have a population, then you can start to learn more about it. And I tackled this question through two papers, one that was submitted in 2020 and one that was just recently accepted. The first I've spoken to you about before, but I will give you a really quick recap. Again, we began this paper. I'll set this up as the title that I had for the paper going into this was a systematic identification of Thorne-Zhitkov object candidates in the Magellanic Clouds. I thought HV2112 was a Thorne-Jakob object, and I wanted to find more. You'll see how that turned out later. But we honed in order to try and find more stars like HV2112, we honed in on one part of it that was really, really spectacular, and that was its variability. This is the light curve of HV2112. So this is time on the x-axis, and then this is how much the brightness changes in a visual filter over time. So it changes by up to 4 magnitudes in amplitude, and it has a 600, so nearly 2-year period. And it has this interesting sort of double peak feature where you think it stopped at the top, but it keeps going. Normal red supergiants, which is what we think Thorne-Jakob should look like on the outside, don't show this kind of variability. So we thought that this was a really interesting aspect to hone in on. Can we find other stars that are red, that are very bright, and that have the same kind of variability, the same kind of light curve as HV2112? I'll be very brief here because I want to get to the second paper, but the answer was yes. We found a group of stars that show the same type of variability. If you look at the blue curves on this plot, these are stars that are showing the same type of variability, really big amplitudes, really long periods as HV2112. So yay, HV2112 isn't alone. We found things that look just like that star. But that doesn't answer the question of what are they? So in order to tell if these stars are truly Thorne-Jakob objects, or if it's the other possible identity, these super AGB stars, through the 2 papers, we threw the kitchen sink at this problem. Obviously, I'm not going to go into absolutely everything that are on this table, but I'm going to go into some of the things that can differentiate between a Thorne-Jakob object and a super AGB star. And the one that I'll bring up in particular, this was sort of the ringer for the first paper, was the mass, or how large, if you put these stars on a scale, what would they come out in terms of kilograms? How big are they? And the reason why this is important is that there is actually a difference in how large you expect these 2 different classes of stars to be. Thorne-Jakob objects have to be 15 times the mass of our sun or bigger. This is a limit from the original theory. If they fall below that 15 solar mass limit, because they're losing mass, they're shedding off mass, for example, the nuclear fusion inside of them will shut down and they'll collapse. So if you see a star in the sky and you think it's a Thorne-Jakob object, it had better be 15 times the mass of our sun or larger, or you have a problem. On the other hand, super AGB stars, these occupy a range generally thought to be between about 6 to 12. We want to get a bit narrower, 8 to 10 times the mass of our sun. So there is a differential here. It's slight, but you expect super AGB stars to be smaller than Thorne-Jakob objects. And in particular for Thorne-Jakob objects, this is a hard limit. Getting the mass of stars, it is a very difficult thing to measure. However, one of our collaborators had a very smart idea to use the fact that these stars are variable stars. And we can basically just use some basic equations of physics of stellar equilibrium. I won't get into the details here, there won't be a pop quiz, but we can essentially relate this P here is the pulsation period. How long does it take the star to go from brightest to dimmest and back to bright again? You can relate that to the radius of the star, which we're able to get that from the luminosity and the temperature. And we get those values from the color and the brightness, just observable properties of the star. And that can be related to the mass, which is exactly what we're looking for. So I'll walk you through this plot bit by bit. What we're showing here is on the horizontal axis, it's in log spacing, but basically this is the period of the star, where longer periods are over here. And this is the radius of the star, so wider stars are near the top. And these lines that are going across, these are lines of constant mass. So if you're a 5 solar mass star and you're pulsating, you have a variability, your brightness is changing over time, you're going to sit somewhere along that orange line on the bottom. And if you're a 25 solar mass star, you're going to sit on the dark purple line that's all the way up on the top. So this is the one aspect that unfortunately the computer system here doesn't like Macs, unfortunately. So this isn't my laptop. And so there is supposed to be a bit of transparency here. But basically, if a star is a Thorne-Jakob object, it has to be above that third line. That third line in the middle is 15 solar masses. Whereas if you expect something to be a super AGB star, it would kind of be around that second line, which is 10 solar masses. So we were able to constrain the masses of our stars. And then just as a reminder, just to put you in my shoes, at the time that I made this plot, this was the title of the paper. I thought we were going to identify more Thorne-Jakob objects. Coming back here. Oh, okay, I'm very sorry, they're not there. This is an issue of the PowerPoint. Okay. None of them were above 15 solar masses. Every single one of them were sitting right about here. I'm very sorry on the Zoom if you couldn't see that, but I jumped to like the 10 solar mass line. I didn't quite reach it. I'm not going to be a good basketball player, but yeah, they're all right around here. Is there a stick? Thank goodness.
Randy, can you admit Doug?
Okay, so all of our stars are right here. And if they're Thorne-Jakob objects, they need to be like here somewhere. But all of ours were right down here. So that's a problem for the Thorne-Jakob object hypothesis. So the takeaway from this is that the current masses of these stars, how heavy they are too low to be Thorne-Jakob objects. And most of them fall into the range that we expect for super AGB stars. A few of them are a little bit less massive. They're around 4 or 5 solar masses, so not quite as interesting. But there's a chunk of about 4 to 6 of the stars that I identified that from this first paper looked to be super AGB stars. So, of course, I couldn't call the paper that anymore. So thus became my first paper, Cool, Luminous, and Highly Variable Stars in the Magellanic Clouds from Assassin, which is that's the telescope that we used for most of this. Implications for Thorne-Jakob objects and super asymptotic giant branch stars, because you do want to hedge a little bit. And while we took a fair amount of analysis in this first paper, so this is how the rest of them filled out, you'll notice the mass is really the only thing where we're saying this is showing that these can't be Thorne-Jakob objects. And while that was a pretty compelling argument, you know, that minimum mass for Thorne-Jakob objects, that's theoretical. That's based on the original theory from the 1970s and the 1980s. If that minimum mass could be a little bit lower, then suddenly we have a problem. So thus began the second part of my project, the second paper, where we're digging into some things that we think that could really help us tell if these stars are Thorne-Jakob objects or super AGB stars for sure. So the first two I'll take together and just talk about kind of briefly. So if these stars are Thorne-Jakob objects, a supernova had to have happened in that system. You've got to make the neutron star that eventually ends up inside the red supergiant. And a supernova will do one of two things. If the supernova is asymmetric and there's a velocity imparted to the neutron star and then therefore the red supergiant that it runs into, it can give a kick to the star and it will kind of start to drift away in a direction that the stars around it aren't moving in. And with the Gaia satellite, which some of you may be familiar with, this is a satellite that very precisely tracks the motions of stars across the sky, very, very, very precisely. So we're able to tell if the stars that we care about, this group of candidates that I identified, if they're maybe moving in a weird direction compared to the stars around them, which maybe implies that they got kicked by something like a supernova. And the second thing that we can do, if the supernova didn't impart a kick, if the Thorne-Zhikov object stayed close to where it was born, you might expect there to be a supernova remnant. So I'm sure you've possibly even observed yourself some beautiful supernova remnants in our galaxy or elsewhere, like the Crab Nebula or Cassiopeia or others. So when stars explode, they leave behind a whole lot of debris. Eventually, they will start glowing in visual wavelengths like these, but early on, they're very bright in radio wavelengths. So I searched the areas around our stars using radio surveys to try and see if there were any bubbles essentially around our star that indicated the shock wave of the supernova spreading out and pushing material away from it. And the answer for both of these, for Gaia kinematics, it's tricky, unfortunately, because the neutron star that is created by the supernova gets kicked into a red supergiant. Red supergiants are very large, hence the name. So another star being kicked into it, it might move it a little bit, but the speed that it would move at would be very small. And unfortunately, since the stars that we're looking at are in the Magellanic Clouds, which are outside of our galaxy, the amount that we would expect them to move on the sky, even if they did have a supernova kick, would be too small to see with Gaia. So that was a little bit inconclusive. For supernova evidence, I similarly didn't see anything in radio. I didn't see any bubbles around the stars. However, supernova remnants in radio don't last for as long as we expect Thorne-Zhikov objects to live for. So it's possible, although unlikely, that we're just catching this group of Thorne-Zhikov objects very close to the end of their lives when the radio emission from the supernova remnant has faded, but before it starts to turn up in the visual. That's possible. Statistically, it's unlikely, but not enough for us to put a big red X over this one. However, there are two more things that we tackled in this paper, and these ended up being pretty compelling. So the first is the star formation history. So what I mean by the star formation history is that if you look at a galaxy, this is the large Magellanic Cloud in this image. If you look at an area that has a lot of bright blue, young, massive stars, you know that a burst of star formation had to have happened recently, or recently in terms of cosmological timescales, like near the edges of the Large Magellanic Cloud here. Whereas if you're looking in an area that has mostly red stars, small, old red stars, like down here, for example, there hasn't been recent star formation there. And because Thorne-Zhikov objects, they're progenitor systems, as we'll call them. A Thorne-Zhikov object was originally two supergiant stars, whereas an AGB star is a giant star, which is smaller and therefore older. So you can essentially expect, if you're looking at a Thorne-Zhikov object, you wouldn't expect to see a TZO in an area with no recent star formation. That wouldn't make sense, because there had to have been relatively recent star formation to make two supergiants, one of which has already exploded. So we were able to use star formation history maps of the clouds, and you can see here, this is from this paper that we used. This is the LMC. It's been divided up kind of into all these little boxes, and each of those boxes has a star formation history in terms of time. I did this in collaboration with a collaborator from Ohio State University, and I'll go through some of the expectations for this, but typically, generally what we're looking for is that we would expect, if these stars are Thorne-Zhikov objects, that they would be in areas that have younger star formation histories. And if they're AGB stars or super AGB stars, they'll have older star formation histories. Yeah, sorry, that's exactly what I just said. Yeah, so if we think that they're Thorne-Zhikov objects, we would expect them to be in areas that are similar to red supergiant binaries with more recent star formation history. Whereas super AGB stars, we just expect them to be with the giant star population. And I apologize again, it seems like Windows does not like transparencies. There's supposed to be lines connecting all these. So just briefly, take these red dots here. These are red supergiants. Imagine that there's a line connecting all of these. It comes up and then it comes down again. You can see that red supergiants are over here on the left-hand side of the plot, which is younger times. This blue diamond all the way up here, these are AGB stars or giant stars. So you can see they're doing nothing down here, and then there's a big peak right here. So red supergiants are peaking at younger times, and giant stars are peaking at older times, which is good. If it was the other way around, we'd have a big problem. Our stars, our sample, is in gold. And where is the highest gold point? Right along with the giant stars, and not along with the red supergiants, which are the stars that make Thorne-Jakob objects. So the local star formation histories of these stars are more consistent with giant star populations and not the populations that make Thorne-Jakob objects. So that is, in my opinion, another red X for the Thorne-Jakob object hypothesis. And finally, we have spectroscopy. So spectroscopy is complex. I'm just going to be giving the key results. I'm happy to chat about the details to anyone later. But just to quickly go over how spectroscopy works. So when you look at the light of the star, you can look at it all together, which is called photometry. You can get a magnitude from that, or you can spread light out into all of its constituent colors. You can do this with a prism, and it'll create a rainbow. And if you do it with a prism that gives you enough sort of resolution, you can look for these things called spectral lines. And what happens is that light from the star, which is just white light with all the colors, it will run into elements that are in the atmosphere of the star. So elements like hydrogen and helium and iron, for example. And those elements will block out certain wavelengths of light. Each element has its own unique fingerprint as to which colors or which wavelengths of light it blocks out. And then only certain wavelengths make it out of the star and make it to our telescopes. And you can see in a similar spectrum here that the colors that are missing from the original spectrum, so like red and the blues and violets, have these dips in the spectrum. The light is missing because the light at those particular photon wavelengths hit a molecule of hydrogen or it hit a molecule of iron. So that's how spectroscopy works. For Thorne-Jakob objects, you have a neutron star inside of a red supergiant. And the atmosphere of that neutron star is incredibly hot. And that's where all of the nuclear fusion is happening, actually. It's not happening in the core, like happens in our own sun, but it's happening in the atmosphere of the neutron star. You make elements like lithium and really heavy elements like rubidium and molybdenum. These are not elements that you expect to see in normal red supergiants or even stars like our own sun. You would only expect to see this in terms of something that looks like a red supergiant for a Thorne-Jakob object. And then they're pulled out to the surface due to convection. For super AGB stars, so I mostly do massive star research myself. Giant stars are considered to be low mass stars. So when I was doing this project and suddenly I had to learn a whole lot about how giant stars work, I discovered very quickly that the nucleosynthesis of low mass stars is way more complicated than it is for high mass stars. So I'll just be going over some key points, and in a moment, I'll just tell you what the differences you expect between them are. You have an early and rapid enrichment of lithium, which again, you don't expect in red supergiants, and heavy elements that come from something called the S process grow over time. And in particular, you get a pileup at atomic number 37, which very conveniently is rubidium, which is also an element that you expect to see in Thorne-Jakob objects, but you don't expect quite as much as other elements like molybdenum due to the nucleosynthetic processes there. Yeah, this one. So in order to get the spectroscopy of these stars, if you've been to my previous talks, you may have seen these photos before, but we traveled to Chile to the Las Campanas Observatory, which houses, among other excellent telescopes, the twin Magellan telescopes. So these are two 6.5-meter dish telescopes. This is a photo that I took at night while we were observing, where you can see the heart of the Milky Way galaxy over top of one of the domes. This is what it looks like in the day on the outside, and this is what it looks like on the inside. So I was like, I knew, I looked it up that, okay, this is a 6.5-meter dish. This is really big. Have you ever thought that you've known how big a moose is, and then you actually see a moose in person and you're like, oh, okay. That was my reaction with this telescope. It's way bigger than what you think it is. So this is me for scale, and I'm standing quite a bit in front of the telescope, and even with that angle, like force displacement, my head isn't even reaching the bottom of it. So this is a huge machine, very, very impressive. And we spent a lot of nights taking a lot of data, myself and my collaborators, along with the telescope operators, because, you know, I am not driving this around because that would be silly. There's a team of really experienced operators who work at Las Campanas Observatory, and we were able to get all the spectroscopic data. The spectra are very complicated. There's a whole lot going on. There's lots and lots of lines happening. So I'll just remind you, if these stars are Thorne-Jakob objects, we expect a lot of lithium, a lot of molybdenum, and a lot of rubidium at the same time. If they're super AGB stars, you'll get a lot of lithium early, and then you get heavier elements a little bit later, but you can have a little bit of overlap. And particularly, you expect a big pileup of these elements around rubidium and not quite as much molybdenum. So in these plots here, I have these three elements. These red circles down on the bottom, these are red supergiants. So for each of these elements, we expect them to be doing nothing special, nothing in particular. And our stars that we care about are these sort of colored icons. So in particular, the big takeaway here is that nearly all of our stars have a lot of lithium in them when you compare them to your bog standard red supergiant. So that's a good sign. If you look at rubidium, there's also a lot of rubidium in most of our stars. And then if you look at molybdenum, however, most of these icons are down sort of in the crowd with the rest of the red supergiants, except for one star. There's this one guy. It's the blue star. Which star is the blue star? It's HV2112. Because of course it is. So the core takeaway here is that most of the sample is consistent with super AGB predictions. Some of these are likely slightly lower mass 4 or 5 solar mass AGB stars, but still quite interesting. HV2112 remains an outlier. And I will highlight that HV2112 remains an outlier. I'm going to show you some of the slides that I was showing you previously. Unfortunately, some of these aren't going to come out quite well because they were the ones that required the transparency, but I apologize for those on Zoom, but I will try to notate this with my stick. HV2112, the area that it was sitting in terms of mass, was right about here. It's at about 12 or 13 solar masses. So below this minimum 15 solar mass limit for Thorne-Jakob objects. But as I said, that's a theoretical minimum. And that theory comes from our understanding of things like how convection works in stars. And spoiler alert, astrophysicists do not understand how convection works in stars very well. You can tweak the parameters a little bit and get the minimum mass for a Thorne-Jakob object down to 10 solar masses without playing too much with the physics. Most of the rest of our stars are around 8 or 9 solar masses, so this wouldn't affect them, but HV2112 was the biggest star in our sample, even when we were finding other stars that looked like them. For this one right here, this was the star formation history. So if you remember, I said that our stars were peaking. They peaked up here along with the giant stars. But some of you may have noticed there's an asterisk next to this sample. And the reason is that these gold points here, this is my sample of stars, these candidates that I care about, except in this plot, there's one star that I didn't put in that sample. This is what it does if you don't include HV2112. It peaks really strongly and really nicely with the giant stars. What happens if you put HV2112 back in? Hello. Suddenly this peak drops because as a fraction, there's fewer stars here at old times. And suddenly it's saying there's a not insignificant amount of signal, for lack of a better term, at young formation times, right around where you expect red supergiants to be, which are the progenitors of Thornjakov objects. So the asterisks are here because HV2112 remains, I'll say it diplomatically, ambiguous. I still think that HV2112 is the best candidate for being a Thornjakov object. I don't think it's settled. I think that our work on constraining the mass needs to be explained. And most crucially, if HV2112 is a Thornjakov object, you need to explain why it has such huge variability that you don't see in red supergiants. But that's a call for modelers to make modern models of TZOs, because that should have happened years ago. But for the rest of our stars, if you forget about HV2112 for a moment, everything comes up gold for them being super AGB stars. Yay. So, and this would be, as I mentioned, there was one really strong candidate TZO candidate super AGB star when I began this project. And not my full sample of 10, but I'd say there's about 5, maybe 6 that are really strong super AGB star candidates. So again, these are the stars that sit on the dividing line of will they, won't they? Will they explode as a supernova or won't they? And having a larger population of these stars to analyze is really important for many areas of astrophysics and to test our models and so on. So that was my second paper. I went for sort of the part 2 vibe here. So cool, luminous, part 2, spectroscopic and environmental analysis of Thornjakov object and super AGB star candidates. And I have to still say both words because HV2112 will not make up its mind about what it wants to be. So that is, one second, just let me, that was an old slide, sorry about that. So these are the names of all of my collaborators. In particular, Maria Drought and Brian Gainsler are my supervisors at the University of Toronto, who are incredible. And I will leave you with a little bit of an artistic interpretation. This is not a photo, this is art. This is digital art done by my roommate. I asked for the small Magellanic Cloud with my 6 stars and HV2112 really bright, really beautiful. Because this is kind of how I feel about the project. And HV2112 is bigger and more special than the others because, well, you know why. So that is everything. Thank you all very much for listening. And I'll be happy to apologize for some of the graphics not working out, but hopefully we're able to get the.
And I apologize too.
No, that's okay.
We're still figuring this out. That was wonderful, and I'm sure you'd be happy to answer some questions. It's fascinating to see how much work goes into settling these really important questions and finding, you know, something that really isn't. And these are new objects. You think that we know something about stars, and you're discovering new objects, but it takes a lot of work, and it's really impressive to see how much work has been done and how much that you've done. So questions from the audience?
And I also have the chat up, so if people on Zoom have questions, I can also see that.
Well, I've got a quick question. So and I probably asked this before, but I forget what the answer was. And you focused on the Magellanic Cloud, I guess, because so why would somebody have looked at that one little star out of all the stars that are in there, you know, the HV2112 to start with? What got their attention?
So that's a great question. And that's a really interesting story in the community. So the original paper that identified HV2112 as a Thorne-Chekhov object candidate back in 2014, that was led by Emily Levesque, who's a professor at the University of Washington in Seattle. She was originally doing a totally separate project where they were trying to constrain how cold can red supergiants get. Red supergiants are among the coldest, they're still 3,000 degrees Kelvin, but they're among the coldest stars in the universe. So they were looking at lots and lots and lots of red supergiants. The reason why it's in the Magellanic Clouds is that at least before the Gaia satellite came out, getting the distance to a star was really hard and really complicated. If it wasn't in a binary or something, it was really hard. Whereas these Magellanic Clouds, they're so far away that you can just, we know the distance to them, and you can kind of assume that every star in that galaxy is at the same distance. Because, you know, if something is 60 miles away from you or 60 miles and 1 inch away from you, it doesn't really matter. So they were looking at red supergiants in the Magellanic Clouds, and in their paper, they noted that a few of them were a little bit weird, had, you know, temperatures that were really low, had really bright luminosities. And Anna Zhikov, one of the 2 sort of co-founders of the theory, contacted Emily Levesque and said, hey, those red supergiants in your paper, those look weird. Can we get some spectra of them? Can we see sort of what's inside? And that is how it was first identified as a TZO. So it actually was Anna Zhikov who directly led to the first candidate being identified, which I really like.
Yeah, so that, I mean, that's because I've been retired now that I forgot about that aspect of it. But there's actually a lot of things, you know, the whole business of being able to measure distances to other galaxies depends on the same thing that people found. Variable stars, the Cepheid variables in the Magellanic Cloud, knew they were all the same distance. So if we didn't have the Magellanic Clouds, we wouldn't know as much stuff as we know, right?
If we didn't have the Magellanic Clouds, I think we eventually would have figured it out, but we wouldn't have figured out things like the fact that the universe is expanding at the time that we did. Because Henrietta Swan-Leavitt coming up with the Cepheid period luminosity relationship for distance, and then being able to apply that to further galaxies. If we didn't have that middle step of this galaxy that's like in our backyard, but not across the street, not only would it have put back our understanding of stars for a really long time, but that would have put back our understanding of most things in astronomy. So yes, I'm very glad that we have these 2 satellite galaxies.
Cool, yeah.
Is there an example of one of these neutron star red giants in our own galaxy?
So there is a really good candidate. It was identified, I think, in 2021, so just after my paper had come out. I think it's VX Sagittarii, so the VX star in the Sagittarius constellation. But there's a really nice paper about it, and it's a really bright red supergiant that has the elements that you would expect a TZO to have. So there's one really good candidate in our galaxy.
Okay, so Robert, and then we'll get a question from Peggy.
I was just wondering, with those weird stars, when the neutron star is kicked and heads toward the red giant, well, the red giant did have its own core. So that would then, I suppose, increase the mass of the neutron star itself. Does that have any effect to change the behavior of the neutron star? Or would that have something to do maybe with the variability?
So would you be able to paraphrase that question for the people online?
Yep. So the question was, so the neutron star is kicked into the red supergiant, but that star has a core of its own. So what effect does that have on the neutron star, and could that lead to the variability? So to answer the first question, that has a big effect. So what ends up happening is that the neutron star travels through the red supergiant and eventually meets and merges with the core of the original red supergiant, which at that point is kind of like a proto-white dwarf. It will increase the mass of the neutron star. If it increases the mass of the neutron star too much, then you can have a collapse into a black hole. I'm not quite sure what that would look like, but that would be very interesting. But for the scenario where it forms a Thorne-Zhikov object, both the neutron star and the core of its companion are small enough that that doesn't happen. So yeah, it merges, but it is able to remain stable. And then in terms of the variability, I actually don't know. And that's one of the things that I really hope that like modern theorists will look at. We know that we don't see really big variability in red supergiants, but the structure of a red supergiant and the internal structure of a TZO are completely different. So I think it's possible that the neutron star, being such a hard surface inside of the supergiant, I think it could help the variability, but I actually don't know the answer to that question. That's still an open question in my mind. Thank you.
Hey, Anna, could you scroll up to Peggy
Yeah.
Dixon's question first?
Yep, so Peggy Dixon, I'll read it out loud just for everyone. If you could acquire any types of data, which would be the most important for helping settle this question? Oh, this is good.
That's a great question.
That's a great question. Okay, so in terms of data, so for me personally, I think the most important thing to settle the question would actually be improved theoretical models. That I think would help the most. But in terms of data, I think higher resolution spectroscopy, we had really high resolution spectroscopy, and it still wasn't quite enough to, there's still some open questions that we have basically about the what we're seeing in the spectra. So yeah, I would say slightly better spectra. That's a very good question. Thank you.
And I think Chris has
Chris had a
one.
question. So this is from Chris Stevenson. I would think that using pulsation period to determine the mass of single pulsating stars is a bit uncertain. How much does that affect, for example, with metallicity, does that have on the masses you determine? Excellent question. Thank you. So one quick second. I'm going to attempt to, because I have backup slides for this exact question. Where did they go? Yes, okay. So taking,
Okay, we're back on mine, so we need to share. Oh, there we are. Perfect.
I think that is.
No, you're good.
Yes, okay, we're good. So if you remember the equation that I had there of pulsation period, what we're essentially doing is we're comparing two models. So we have models of giant stars from about 5 solar masses up to about 7 or 8 solar masses. So we have very, very, very detailed models of how stars of a few different masses change as they evolve, how their temperatures and luminosities and how their pulsation periods change. And essentially what we wanted to do is we wanted to scale those models up to like 8, 9, and 10 solar masses for the super AGB stars and 15 solar masses for the Thorne-Zhikov objects. And we did that by essentially making, that's not too hard to do for changing like a 5 solar mass giant model to a 10 solar mass super giant or super AGB star model. But for Thorne-Zhikov objects, we basically, this was our theoretical collaborators who came up with this, which is brilliant. If you look at the overall structure of a Thorne-Zhikov object, you have this huge, big, puffy convective envelope, mostly hydrogen. And then you have this incredibly dense, it's made out of degenerate material because the atoms are so tightly packed, you start getting weird quantum mechanics business, a very, very dense neutron star core. If you look at a super AGB star, you have a really big puffy convective envelope made of mostly hydrogen, and you have a dense core that is essentially a proto-white dwarf. It has oxygen, neon, and magnesium, which are burning materials left over. But if you don't look too hard, the structure of a super AGB star and the structure of a TZO are quite similar. So we essentially made the argument that you can get out these structure constants, this alpha and beta, which if you remember, I'll just go back to it here, are part of this equation here. The alpha is in front and then the beta is near the end. So this is a fundamental equation of stellar pulsation. If a star is pulsating, it will follow this law. And we know that our stars are pulsating because we see how much variability that changes. The question is, how confident are we? The questions that essentially make up the uncertainty here is how confident are we in the period of these stars? We're very confident because we just need to see how long it takes for it to get bright again. How confident are we in the radius? We're relatively confident there. It is difficult to constrain physical parameters like that, but you can work that out from the brightness and the color. And then how confident are we in these structure constants? And by making the simplifying assumption that the structure should broadly be the same, we're pretty confident. Do I think that maybe it's possible that you could bump the mass of H3212 up by like a solar mass? Like, is our uncertainty, is it possible to get it up to 15 solar masses? I think for H3212 it's possible. You definitely wouldn't be able to get all of our stars up there. But yeah, in terms of overall uncertainty, I'm pretty confident in it, but there is some uncertainty. And this is, again, part of why I would love for there to be modern models of Thorne-Jakob objects. And then in terms of the metallicity, we used models that were from, these were models of giant stars in the small and large Magellanic Clouds. So we did account for metallicity.
So, and for some of us know, but some people don't. For Anna, when she says metal, she means everything heavier than helium.
Oh,
right?
yeah. This is actually, I actually think I have a backup slide even for that. Kind of, yeah. This is for something else. This is explaining where every element comes from. Astronomers, we call them hydrogen, helium, and metals. This is because almost everything in the universe is hydrogen and helium. There's not a whole lot of everything else. And especially when you consider the Big Bang, things that were synthesized at the very beginning of the universe, you get a whole lot of hydrogen, get a bit of helium, and then a tiny, tiny trace amount of like lithium. So yeah, things even like neon, which is, you know, a gas most of the time, we call that a metal. So when we talk about metallicity, that is asking what percentage of the star is not hydrogen and helium. And this is important because that will affect how the star evolves. And in particular, the Magellanic Clouds, those satellite galaxies of our Milky Way, they have a metallicity that is a little bit lower than the Milky Way galaxy, which actually makes them really interesting laboratories. Because if you consider stars, the first stars must have been only hydrogen and helium because that's all there was around. And then as they blow up, they pollute the universe with their metals and those make new stars. So looking at the Magellanic Clouds, it allows us to look at essentially almost what the universe would have looked like if it was a little bit younger, if there was a little bit less of all this other stuff going around and it was mostly just hydrogen and helium. And I realize I went on a whole tangent about cosmic nucleosynthesis there. But yes, that's why we call them metals. It's a little silly, but.
Nicola, great presentation and congratulations on the paper.
Thank you.
It sounds like one of the deciding factors to sway you towards thinking that HB2112 is probably a TZO versus a super AGB was the spectroscopy and the detection of molybdenum on the surface.
Mm-hmm.
It almost sounds like that was one of the major factors, and you know, if that hadn't been the case, then perhaps it would have been, you know, more ambiguous.
Yep.
So I'm just curious, and you kind of touched on that already with, you know, wanting better theory and better, you know, modeling of theory. But how confident are we in that factor, you know, the presence of molybdenum being more characteristic of, TZOs.
And maybe if you could just repeat the question.
Yep.
Summarize quickly.
Absolutely. I'm just going to go back to the plot as well. So the question is that for H22112 in particular, and I'll highlight it right here, one of the most important factors in me still being sort of undecided about what this is that it still shows a significant amount of molybdenum, whereas none of the other stars do. And basically, how confident am I in this sort of being a deciding factor? In terms of expecting Thorne-Zhikov objects to have a lot of both rubidium and molybdenum, I'm as confident in that as I am about anything with the Thorne-Zhikov object theory. Maybe with updated nucleosynthesis models, it would totally change, but with what we're able to say right now. However, just to put another spanner in the works, if you get to the absolutely most massive super AGV stars, so you are on the edge of the plank about to tip over into blowing up as a supernova, but you're still technically a low mass star. This would be like a 12 solar mass super AGV star. Our understanding of the nucleosynthesis in those stars is not good because it's really, really complicated. And it is thought that maybe you could have higher levels of burning that would end up producing molybdenum. So in my paper, I basically say HV2112 is either a Thorne-Zhikov object or it is the biggest, like most extra super AGV star that it can be. I think I still lean a little bit more towards Thorne-Zhikov object, but that might just be, might be like several years ago, Anna clinging to that original paper title of like, maybe it's a TZO. But yeah, thank you.
Yeah, I guess the number of nuclear reactions that you have to keep track of, and you need to know something about the rates for every one of those reactions. It must be just enormous in these systems.
It's huge. And like I was just taking a very surface level approach of like the theorists are telling me that I look for these three elements. And even doing this was a nightmare. It ended up being the most rewarding, but this was the worst part of the paper. I was doing all this spectroscopy. But yeah, it's nucleosynthesis in stars is really hard. I'll just say that.
Cool. Well, any other questions?
I don't have a question.
Okay.
But you're just thinking, oh dear God. I just have a thank you to all of you for asking Anne to come during COVID. Of course, it's been many years since I've seen her present. The last time was here. And thank you for your thoughtful questions, because they are very thoughtful and it's a true sign of how much you all got it. And yeah, she's spoken at Harvard a couple of weeks ago. She's going to Seattle after Christmas. Yeah. And this is her favorite. I'm going to tell you that.
It is.
It's great, and your questions are so thoughtful.
Harvard was cool, but you were cooler.
Yes.
Well, we really appreciate it. You have an open invitation. You'll probably have some more stuff to tell us about pretty soon. So.
I was joking. I talked to my supervisors this morning and I told them, yeah, I'm talking to RASC tonight. And I joked, I said, I'll give my like last talk when I retire to them. And it'll be like the 20th time I've spoken to you all in many years.
Well, I think you're our favorite speaker. You're certainly our most regular speaker. So thank you very much. And we got a little gift for you.
Thank you. I have a space calendar in my office and it's about to run out. So this is perfect.
Well,
thank
perfect.
you.
Okay. And I'm wondering, does your thesis title have a question mark in it then?
No. So no, my thesis title has to change. So funny story. The Thorne-Zhikov object part of my thesis was supposed to be like a short 1-year project of like maybe like 1 20-page paper. And then 4 years and 2 35-page papers later. So I don't actually know what my thesis title is yet.
Yeah, I was wondering about that. I was watching this and thinking, it's probably not written in stone yet.
No, not yet. But I'll know. Well, I need to know soon. So. Yeah.
Well, that's fun. Great. Thank you very much again.
There's thank yous online.
What's that?
There's various thank yous online.
Okay. And I'm going to.
Okay.
Is this screen visible online now?
Yeah.
Perfect. Okay. We did some holiday gift suggestions last time. I don't know if anybody's got any more. Randy.
The telescope I mentioned at Costco will probably drop by $60 a few days, or just after Christmas. So, $259.
Oh, it's $199 today.
Is it? Okay.
Okay, so Randy's saying that the telescope he mentioned last time is going to drop, and Gary said it's 199 now.
Yeah, it was.
Okay. And actually, Cynthia and I were shopping at the dollar store today, and you wouldn't think that you'd find something that would be a gift suggestion for this group, but there was actually a little, it didn't have any mechanisms, but it was a little model of the solar system. So no gears, so you had to move the planets around yourself, but it turned out you also had to paint it. So if it had actually been painted to start with, I probably would have brought one and set it up here, but I didn't have time to paint it before the meeting. So if you want a stocking stuffer, you can get the solar system there. Okay, so well, that was $5. It was high-end stuff. Okay, so we do have a few member observations. It's been because we're a little bit earlier in December, it's been a slightly shorter month, and there haven't been that many clear nights. And but we do have a few member observations, and I'll ask Bernard to get ready because he actually caught Mars just before it went behind the moon. So this was last week and just after it came out. So are you there, Bernard?
Yes, I am. Can you hear me?
Yeah. You want to tell us a little bit about this? You're the only one around here that got a picture like this, and you got it at both ends.
Yeah, well, I was very lucky. Actually, last week I was off work with sick with COVID, and I was up late one night there. That was the night that this was happening. And actually, I was watching it online, and the weather, as you know, was calling for rain, fog, and drizzle. And so just as it was getting close, I went outside a few times just to have a look. I could see it was clearing a little bit. So I grabbed my camera there, my old DSLR Pentax with a 300mm lens, and went out and started taking a few pictures. And it ended up, I was lucky enough that it cleared off enough in between the clouds, and I kept those two exposures here, I guess you call them, and just as Mars was going behind there, and I waited. I think it was probably about 40 minutes or so, and I was watching the HAP online there, and watching the Sky Safari actually, and to see when it was going to come out, and it was dead on actually, and so when it came back out, so you can see, you know, from my location where Mars went behind the moon and where it came back out. So it was pretty interesting. I guess it's different all over the world. I know some people had it online there, just skim by, and I guess it all had to do with where you were too. But that's yeah, that's where it was from my location out there in Central. So how far it went behind, and how long it took.
Yeah, well, that's pretty cool. Congratulations.
Thank you.
Okay, and Jim has a shot of quite a wide angle shot. You want to say just a few words about this one?
Hardly remember that now. Okay, that was
just after our last meeting.
Yeah, that was shot with a 90mm macro lens, as I recall. Yeah, and I managed to get a few exposures of that, 2 minutes. And it was basically with a focal length of only 90 millimeters, you don't need much in the way of tracking accuracy. So this is unguided on my telescope now, and processed and stacked in PixInsight as I would normally do. But there are a number of different objects. This is along the Milky Way. This is Cygnus, and the bright comet-looking feature at the top of the picture there is basically that's Deneb, and to the left of that is the North American Nebula and the Pelican Nebula. Then down towards the to the center right, there's basically the Saturn. I think that's the Saturn region, which is a highly nebulous region. And then down towards the lower left, there is the faint Veil Nebula and the Cygnus Loop Nebula.
Yeah, you rarely see them that small on a picture.
Yes. And so yeah, there's a fair bit of interesting detail in there.
Okay, and I apologize to the people online. I'm not going to repeat everything that Jim said, but you could hear it? Perfect.
We could hear it.
Okay, good. Sorry, go ahead.
Was that taken close to where he lived or on the east side of St. John's? Or was that?
Geez, I don't remember, but it's my secret. Yeah, no, I think I'm not going anywhere. This is definitely from Pleasantville.
Okay, from Pleasantville. Okay, this is one of Chris Stevenson's Mars pictures. Anything you want to say about that one, Chris? Chris there.
He was on.
Okay.
Can you hear me now?
Yes.
Ah, okay. The spacebar wasn't working. Yeah, thanks. There are two. I actually trust the other one better. This one's got sharper edges around what looks like Antarctica.
Okay, yeah, the other one's coming.
Yeah. Yeah, these are just two quick attempts as the clear skies and so on permitted to catch Mars when it's high up in the sky from the backyard in East End, St. John's. 12-inch Meade telescope, same telescope as Bernard's actually, and the little QHY 53462C, the planetary camera, the little blue eyepiece camera that everyone's using. Very, very sensitive little camera. About the only thing I can say is that I used it without any filters at all, and this camera is near infrared. Thanks, Bernard. This camera is near infrared sensitive, and so for ordinary RGB colors, they're a little washed out. It's kind of orange heavy. So if you're expecting white polar caps in my photos, you probably won't see them. But yeah, so this is one of two. And the other one, I think, was a couple, maybe a week later. I forget the date.
Yeah, we've got a lot from that night. That's the same night that Jim took his picture.
Ah, okay.
19th, and here's your Jupiter from the same night.
Oh, yes. I'm actually pleased with that one because there's the hints of detail on Ganymede, which is the one on the bottom right.
Yep. And so I think your next one's coming up after a couple. So I guess we then had about 6 days, and I tried Mars. I don't have the same kind of setup, but I was quite happy to see a little bit of detail on Mars. That's using a Dobbs, so no tracking, just drifting through and doing a video.
Much better polar cap.
Yeah. Yeah, so there's a polar cap there. And then the next one, I think I got it right. There was a fireball, and I think this was your all-sky camera. And I'm guessing that little white square where I've got the red arrow is where the fireball was?
Yes.
So this is a gazillion pictures taken
overnight. And that was totally wiped out. And Dave Newberry's camera, he had two cameras, and he had just the one frame totally out at the same time.
Yeah, so that's really interesting.
That was CBC. We're talking about the fireball, the night of the fireball. November 26th, you asked about fireball. It said CBC radio said that they're.
Yeah, they were asking about,
Yeah.
Did anybody see the fireball?
But it seemed like all the cameras were wiped out. Usually you can see the fireball. So it must be
And I
pretty
think on one of the sort of cameras that looks over the city, you could see the flash too.
See it in the harbor,
Yeah, the harbor camera.
right next to that, big light on the.
Yeah.
Well,
Anyway, so yeah, I thought that was really interesting. Thanks for that, Gary.
there's a comment on the chat. Bernard says excellent cars.
Yep. Okay. Yeah. Thank you. So what Randy was just saying was Bernard had a comment about Chris's Mars, said excellent. Okay. A few days after that, I went out with my Dobsonian and did the moon and another Mars and Jupiter. And I was really happy with Jupiter because I've done lots of pictures of Jupiter, but rarely get the red spot where I can see it. And for people who are into that sort of thing, oh, you can't really see it on the screen here. There's a feature here where two intersecting ridges get illuminated on the terminator, which you can see on the computer, but you can't really see on the screen. And then I think we get back to, so Chris, this is the other Mars that you want to know?
I think that's the same one.
Oh, I screwed up. Okay, sorry.
That's okay. The second one looks similar, but just has softer edges. But
okay.
I believe in the detail more. The Syrtis Major sticking up to on the left, upper left. Sorry. Anyway, and Gary is the Mars surface detail person, so he'll be able to point him out to the other one.
Okay, sorry about that. I thought I had gotten the. Yeah, I must.
No problem. Thanks.
Okay, and the next one is one of mine too, and Jim Johnson loaned me a camera with the infrared filter removed, so a modified camera with a light pollution filter in it. So it took me a while to figure it out because you have to actually push buttons rather than using the touch screen. So I only got 11 minutes, but I tried it out just about the last time we had a clear night. And I was pretty impressed. So I'm looking forward to the next clear night. And this one's Cynthia's picture of the moon and Jupiter at Marion Bright at the Botanical Gardens with some guy standing in the corner.
That's Santa. That's
yeah.
Probably Santa.
And John Nugent sent in this nice picture of M45, and John is a proponent of long integrations. He gets lots of light into them, so that's very nice. You want to say anything more about that one, or?
No, just that I'm still working on another edit for it.
Okay.
With some of Jim's tips and stuff that he showed me. You just try to get rid of that line too that goes through.
Yep. Well, there's a lot of, you're getting a lot of the nebulosity. I think that's a beautiful picture. So should and you can edit it, but it looks. I'm pretty impressed with it.
I'm already started. I was
okay,
before
good.
I come here, I started it.
Okay, so that's it for what we got this month, and the sky this month isn't done yet, but it will get done and posted sometime soon. Yes.
You mentioned your library session in case anyone knows anybody might want to go.
Oh yeah, okay. So sometime in February, I'm going to be doing a presentation called Winter Stargazing at the AC Hunter Library. You have to register to get in, and it's it might be Valentine's Day, but I'm not 100% sure. I don't remember. but it's around then. So you can register, if you're interested in that, you can register. You can go to the library website and they have a bunch of these programs that are there. And I'm sure, I don't know if it'll be up there yet, but it will be coming. And so I think that's just about it. Unless Anna comes up with something in the next 3 weeks, I'll probably be giving the talk in January. And I'll talk a little bit about the Lucy mission, which we've got lots of time to talk about that. It's going to take 12 years to sort of go through the whole cycle of things it's doing, but I'm really fascinated by all the jigs and reels that it's going through. So it's a probe that's on it. It was launched a little over a year ago. It's already traveled away from the Earth and then back to the Earth. It's going to do that one more time. Then it's going to head out to the orbit of Jupiter, but not at Jupiter. It's going to be way in front of Jupiter, visit some asteroids, and then come back to the Earth, then go way behind Jupiter, visit another asteroid. So that's what I'm going to talk about in January. So that's it. We have some holiday treats. This is our holiday meeting, and we finished in time to actually enjoy some of them. So we'll uncover them in the next minute or so. I'd ask you to maybe use the hand sanitizer over here before you start handling things. And we do have little tongs on most of the trays. And it's always a good idea to practice, practice good hygiene. That's the word. But under the current circumstances, that's probably even more of a good idea. So thank you very much, and we'll see you in January. Well, we'll see you in the next couple minutes, but formally in January. Okay.
Thank you, everyone. Appreciate it.